Very good. Thanks very much, Dan. I'm very honored to have the opportunity to give the Jerry Faeth Memorial Lecture. It's certainly a high-level list of predecessors. I had some contact with Jerry, I think in connection with the editorship of the AIA Journal, and I was impressed with the directness and clarity. I called him and asked him for some advice, even though I didn't know him very well, and he was just very helpful. I also got a note from Elaine Oran, who was the first Faeth lecturer, and she commented to me that over and over she finds that Jerry's papers provide insight and explanation for otherwise puzzling situations. So again, a high standard has been set. I'll do my best to live up to this opportunity. And I like to give the messages first. So my first message is really about collaboration. So important problems, especially important problems in technology, often go beyond the capabilities of a single individual. So how do you solve these? Well, collaboration. So greater reach, but it's also extra effort, extra overhead. And it's often not the paradigm for universities. You think about monks toiling in their cells, writing individual papers. But even so, there can be a large return on this investment. So that's one message. I'll give you another one. So who am I and why am I here? Well, I'm a technical person, and if you look at the bottom of these things, there's some equations to prove it. This is obligatory. So here's the Gibbs equation, and it's about enthalpy and entropy. Enthalpy is how much work you do. Entropy is how efficiently you do it. So what does a propulsion engineer or power engineer care about? Both those things. And also vorticity, property of rotation of a fluid, and turbo machines, gas turbine engines, the flows are full of vorticity. So I'm a technical person, but I have some exposure to the organizational literature. I have, as Dan said, experience in industry and academia, so I've seen it from both sides. I've also had some experiences with failures in collaboration. Not that the technical work wasn't good, but the whole wasn't greater than the sum of the parts. So I've looked at identification of best practices for university industry collaboration. So that's another theme of my career. Collaboration's been a major part. The mantra, I think, is the whole being greater than the sum of the parts. So it has benefits to the research. It has benefits to the type of problems you can attack. And I'll try to make this point. It gives you different perspectives. And also, it's really important to have informed and intelligent criticism of the work. So in-depth critique is another part of this equation. So I'll be talking about something called the NASA N+3 program, which we were part of, and it's the development of the D8 aircraft. The D is really for one of my colleagues, Mark Drella, and this is really his brainchild, but it's a collaborative endeavor. So it's MIT, it's Aurora Flight Sciences, which is a small company, Virginia-based company, but they have a branch office in Cambridge, very close to MIT, and they're longtime partners. They were started by MIT, former MIT students, and they're longtime partners and teammates, and Pratt and Whitney, as well as NASA. So here's the message, the second message, which is we're working together, all these teams with NASA, on the idea of concepts for a 2035 subsonic transport aircraft. Why do we need that? Well, I'll try to make that point too. So this, to me and to the students, I think, is a really exciting venture. And we take as our mission, impact how industry thinks about aircraft and propulsion, to change the thinking of industry about aircraft and propulsion. And so what I'll tell you about is experiments and computations to climb up. The TRL stands for technology readiness level. It's how mature the technology is. How are we doing in climbing up that ladder? And also the idea that if you talk about new configurations, new vehicles, new aircraft paradigms, you tend to get new problems to work on, which is also an exciting thing. Okay, so there's the three logos. Here we are. And what do universities do? Well, they look at concepts, they educate industry. You can see aircraft and engine design and development, and they bring to the table product knowledge, things that universities really don't have. So this is talking about collaboration not only within organizations, but also across organizations. So you can see the numbers here, 30 people, 25 people, and we're now in the third phase of this, so maybe 8 to 10 people so far, among whom are people from the University of Michigan. And I would say that the program is driven by ideas and technical discussions. So it's the primacy of ideas. So it's what's being said rather than who said it. And we're trying to change these legacy beliefs. Okay, so let me talk a little bit to set the context about the NASA N+3 program. N+3 is generations of air vehicles. So N+1 is the next generation, 10 years. N+2 is maybe 20 years, 25 years. N+3 is further than that. So we're supposed to identify not only the airframes, but airframes and propulsion concepts. What does the air vehicle look like in 2035? So we started out trying to do this in a strategic way, looking first at the scenarios. What might the scenarios be? So the people at MIT who do that, we banded together with them. Then looking at this, advanced airframe and propulsion concepts and the technology needs. So here's the NASA technology goals. And these technology goals, if you see these NASA slides, they'll have changed. But this was the original back in maybe 2007, something like that. This was our marching orders back then. NASA said, here are the technology goals. And look at the fuel burn, because that's what I'll focus on. So 70% change in fuel burn. So what that means is basically that's not much more than just flying the fuselage alone. So if you can do that, that's a substantial accomplishment. And here's the NASA charts of what the N+1 is, forward swept wings. That's supposed to be 2015. Well, 2015, events have overtaken us on that. This is 2025. People are now talking about flight demonstrators for this. Boeing has run their own flight demonstrator. And maybe here's N+3. But ours, well, you'll see what our configuration looks like. But basically, these are stretch goals. And how stretched are they? This is as of 2010. But here's basically fuel burn for different aircrafts, how much fuel is used, versus something called productivity, payload times range. But this is just a way to spread out the data. So we looked at two different classes of aircrafts. And this is the class of aircraft, 737, A320. This is the class of aircraft that's most sold. This is the sort of the largest number of aircraft sold and the highest revenue in this class. So let's look at this. Here's the world's data, and here's the NASA goal here. And to give the story away, here's where we, at least conceptually, here's where we think we reach. So how did we get there? What did we do? And where are we going? That's what I'll try to answer. Okay, so here's trying to differentiate the as-is and the to-be. Engineers tend not to talk about the as-is. You ask them, how do you do something now? And they don't want to tell you about that. They say, I could do it much better, though, if you would allow me to do this or that. So this is the as-is. So one of these is a 707. One of these is a 787. I'm not going to tell you which. But basically, my eyesight is failing at my age, and I can't really tell the difference between the two. So this is 50 years plus now. And if we look at this in another 10 years, it's not going to be greatly different. So not much change in aircraft, a lot of change in engines. So we looked at this in our phase one. And what were the major results? Well, we came out with these conceptual designs. I showed you the performance of the design. And this tube and wing configuration with double bubble fuselage. Why is it called a double bubble fuselage? Well, I'll show you it's wider, but the fuselage looks like two tubes, so double bubble. It has enhanced lift, and it has advantageous geometry for putting the engines on top and in the back. And that allows you to take in some of the fuselage boundary layer. That gives a propulsion benefit. So that's a real plus. And then you don't have to sweep the wings. We fly a little bit slower, so that also gives you a plus. So here's what it looks like. Double bubble. You see that here's the two bubbles here. So here's what the aircraft looks like. Here's what it looks like from on top. There's the seating layout. Here's what it looks like in the back. So here are the engines, the two engines. And so the flow goes over the aircraft. That's the whole run of the fuselage boundary layer. So it's a thick boundary layer. And about 40% goes in the engines. And for this, to stop, we looked at a number of different variations. One is with 2035 technology. One is allowing the wings to, or allowing the aspect ratio to be as large as aerodynamically desired. That doesn't fit in the gate, so you have to say, no, we can't do that because the existing infrastructure won't allow that. So this is with the constraints of existing infrastructure and with 2010 technology. So this was our phase one. So here's what it looks like compared to a 737. So this is the super duper version. Perhaps it's composites, has a much larger wingspan. Takeoff gross weight is less. And this came out to have a 69% fuel burn. The aluminum version flies slow, has a smaller takeoff weight than the 737, was a 37% fuel burn. But you can see the relative sizes of the 737 or the A320, if that's your preference, and the aircraft we're talking about here. And I just have to give my colleague Mark Drella credit, because this wouldn't have been possible without this first principles aircraft design procedure that he put together. It's first principles, so it doesn't rely on correlations, so you can look at new and different, even innovative aircraft, and it allows you to optimize all these things together, airframe, engine, and operations for a given mission. And then you could put these constraints on. So that was sort of the background of it. So our main observations from this phase one are as follows. First of all, what are the improvements due to? Well, there's no silver bullet. You can't say, well, I'll twist the wing a little bit here and I'll get 30% magically. It's like sort of compound interest. So if you look at this, the fuselage is slightly more drag, but lighter wing. Small wing the fuselage has more lift, so the wing can be lighter, smaller, lighter tails. Fuselage boundary layer ingestion, taking in the fuselage boundary layer, smaller, lighter engines, etc. It's like compound interest. Okay. And here's another way of saying, of saying that. This is a complicated chart, but what it's talking about is, this is goodness. Goodness on point of noise, fuel burn, field length, whatever it is. To the right is noise. And these are change in configuration, and this is all the advanced technologies. So what you see here is, where do the benefits come from? Well, the overwhelming part of the benefits is from configuration change. Yes, you go to 2035 engines. Yes, you go to different types of fuselages, airframe load reduction, etc., different types of combustors. But all those things are much less, even added together, they're much less than the configuration change. So that's what I'll be talking about. It's the configuration change. So that was our phase one. Phase two, we said, hey, we have this aircraft that ingests boundary layers. People haven't done that for civil aircraft. That's a major issue. So this integration of the airframe and the propulsion system, that's the major unknown. So our phase two, a lot of phase two was focused on that. What's the fuel burn benefit from boundary layer ingestion? I mean, we could do all the cycle calculations, but if in actuality, if there are some complicated fluid dynamic effects that debit the benefit, it's not a good idea. So we needed to look at that. And along with that, we worked with Pratt & Whitney very closely. We worked with Pratt & Whitney very closely on high efficiency, high pressure ratio, small core engines. Small, that means engines with small gas generators, small compressors, turbines, and combustors that will fit within these new type of aircraft. Let me talk a little bit about this boundary layer ingestion. So it's the fuselage boundary layer. It's the slow-moving fluid been reduced by viscous effects in the boundary layer. And you take the boundary layer fluid through the engine. So it has the potential for improving aircraft fuel efficiency. And it's been used in torpedoes and ships. Ship propellers operate in the wake or in the boundary layer of the hull. And what does it do? Well, it just enables the propulsor to create the thrust, basically to propel the vehicle with reduced shaft power. So that's the benefit. So how does it actually work? So think about two different aircraft. One of them has the nacelles and the engine underneath the wing. So what you do is you create a wake or draft here, low velocity region. That has to mix out, or that mixes out to the free stream conditions. In the boundary layer, you create a high velocity region. That also mixes out to free stream conditions. So you have two mixing processes, the wake mixing and the propulsor jet mixing. The latter is more important. But with boundary layer ingestion, you take in this slow-moving fluid here. You have a combined wake and a jet. And so, yeah, there's some mixing here, but you reduce the mixing losses for allowing the vehicle to do the same thing. Basically, the delta velocity change, if you think about the thrust equation, the delta velocity is the same, but you're starting with a lower inlet velocity. And so the exit velocity is lower. Okay, now what I showed you is a picture of the fuselage boundary layer going through the engines. And so you have a situation in which it's difficult to break things up into thrust and drag. Thrust is, that's Pratt & Whitney. Drag is Boeing, or drag is Airbus. But it's sort of difficult because the fuselage boundary layer goes through the engine, so it's a little bit hard to draw the aerodynamic interference plane. So thrust and drag are ambiguous for these kind of integrated configurations. And you can see the reason here. The propulsor stream includes the airframe boundary layer. And you also have coupled pressure fields from the propulsor and from the airframe. And you have those in the conventional case, but it's much stronger now. So it's hard to make the separation. You have to assume various things. So instead of working on thrust and drag, instead of working on forces, we now work on sources and sinks of power. So again, enthalpy and entropy. Sources and sinks of power. Think about the propulsor shaft power, the mechanical energy you have to put into the flow, and the dissipation. So again, conceptually here, check, we understand thrust, we understand drag. Here, difficult to separate thrust from drag, because the force on this is changed by the presence of that. And the behavior of that's changed by the presence of this. So how do we do that? Well, you work directly with power. So having said all that stuff, one of the things you have to worry about is that now you have a non-uniform flow, right? You have the inlet, looks like this. It's low velocity on the bottom, and it's free stream velocity on the top. So at design point, at cruise point, you're always in a non-uniform flow. So the question that comes up immediately is, what about the aeromechanical limits? Force response, perhaps flutter. What about the decreased fan efficiency? All the things that people have had to worry about before with distortion, but they only worry about that at off-design conditions. But now it's with you on the whole flight. Second one is aerodynamic, or aerodynamic instability here. Does it get any worse with this? Well, those are real issues. So I'm going to talk about now the wind tunnel experiments that we carried out. And so I need to show you this evolution of a wind tunnel experiment. So the first picture, and I'm sorry to the students who came to talk with me at lunch, this is the same slide that I showed them here, but here's two students and Professor Drella. This is in the MIT wind tunnel, and here's a 1/20th unpowered model. It's just a model without any engines. So here's Nina, Michael, and Professor Drella in 2011, and then 2013, and again in 2014, we went to one of the national facilities, NASA Langley 14 by 22-foot tunnel, and here are the same guys. And when this thing was taken, we didn't set it up, especially we didn't pick the day. It just happened to be the day that the NASA photographers were around. But you'll notice that, and I'll deny I said this, if Professor Drella seems to have the same outfit on, Michael Liu seems to have the same outfit on. Nina, of course, is sartorially correct. And that's the end of that. So I'm not going to. So this was our model. It's 1/11th scale. That's about twice the wingspan of me. And it has, you can see, powered nacelles, electrically driven fans. Here's what it looks like from the front. So here's the tunnel, and here's the aircraft. And this is not me. This is the standard MIT 6-foot man. Okay. So we're interested in fan inlet and exit distortion, non-uniformity. We're also interested in assessment of the power input. That's the way we talk about these flows in terms of power. So how did we think about these experiments, or how do we plan our campaign? This is a proof of concept demonstration. Well, you can't really say we proved it, because we haven't done every case, but we demonstrated that it could be correct. So aerodynamic performance, and to do this, the computations which were done which we did in collaboration with NASA Langley, were an important part of this. So it's a back-to-back assessment of boundary layer ingestion versus non-boundary layer ingestion. That's what this is about. It's a boundary layer ingestion experiment, and we can relate the results to full scale using scaling analysis. So we did this at a low Mach number. Now the real thing's going to fly at a transonic Mach number, 0.72, 0.74. But the boundary layer ingestion itself is not Mach number sensitive. The benefit is an improvement in something called the propulsive efficiency. And again, that's about less exit kinetic energy dumped into the air. It's not a Mach number sensitive thing. It depends on the jet velocity ratio, the jet velocity. This depends on what the fan characteristics look like, the fan slope of pressurized versus flow. And neither of those things are very Mach number dependent. And yes, there's a distortion penalty, but the measurements that have been taken so far show that maybe it's 1 to 2%. So if we gain 6, 7, 8, 10% by boundary layer ingestion, even though we might take a hit in fan efficiency, and I don't believe we have to if we design our fans properly, we're still ahead. Okay, so we're trying to assess, we developed this back end with an integrated fuselage. So you see here are the inlets. The fuselage blends into that. Here's what it looks like from the back. This is as installed in the tunnel. And what we're trying to do, again, back to what our overall goals were, quantify the aerodynamic behavior of the boundary layers, develop a methodology which didn't really exist. How do you assess the benefit of an aircraft with boundary layer? How do you do the comparison? Do you do it at constant engine area? Do you do it at constant mass flow? Do you do it at constant exit velocity? So thinking about that in a rigorous way was also an important part of this task. And what we're then trying to do is to define, okay, we do this conceptually. We say, yes, there's a benefit. What are the steps maybe on the way to a flight demonstrator? Something like that. Again, it's moving up the technology readiness ladder. So back-to-back comparison of, I'll show you this boundary layer and non-boundary layer. I'm just saying it over and over again because that was really uppermost in our thoughts. That's the first thing. This inlet flow distortion. What comes into the inlet? What do you have to be worried about in this type of configuration? And also, uncertainty quantification. I'll talk to you about that. And so experiments, computation, and it was very close collaboration with NASA. It was a real pleasure to work in the NASA Langley Tunnel. The people were just excellent. The facility was excellent. There was a really great spirit of teaming. Okay, now I've been talking up to now about the aerodynamic benefits. But there are also system benefits. You can say the aerodynamic benefits are direct benefit. Here's what I measure: propulsive efficiency, things that you talk about in an undergraduate course on propulsion. So those are the aerodynamic things. Jet and wake dissipation, maybe the nacelles are only half nacelles, so you have reduced area. But there are also secondary benefits. Maybe you don't need a pylon because the engines are maybe now mounted on the fuselage. They're very close. Vertical tail, and again, reduced weight. So I'll show you what that, at least I would show you if this thing didn't keep coming back. I'll show you what that looks like in a morphing sequence. And in this morphing sequence, we'll use this TASOP program, which optimizes aircraft to go in steps from a 737 to one of these D8 configurations. So here's what it looks like, and this is fuel burn. So here's a 737 Mach 0.8 with a CFM56 engine. That's the engine that's on all those aircraft. And then you slow it down. You go to here. You have the D8 design with a pie tail. The engine's still underneath the wing. Then you have rear-podded engines here. The engines are now on the fuselage, on the sides of the fuselage. And then you do the podded engines. Now you do the boundary layer ingestion. That's the step we're talking about. So 15%. And then you do a couple more things. Get to 2010 technology. We started off with earlier technology. And that gets you to this 37%. So you can see the different steps. And at each step here, the aircraft is optimized. So at least according to our estimate, this is the best you could do, best you could do, best you could do, marching toward the D8. But you now see where the benefits come from. Okay, so one other equation is that what's the metric? So the savings in the boundary layer benefit is savings in mechanical energy. And the metric, the thing that you measure, is the stagnation pressure. So this is stagnation pressure minus some reference value, and it's times the velocity. It's the flux of stagnation pressure. It means the flux of mechanical energy. So we have this PK thing, and the benefit is PK, the power into the flow, minus the power for non-boundary layer ingesting versus boundary layer ingestion, divided by the PK for the non-boundary layer ingestion. And it's at a given force. Well, what force would that be? Because I said thrust is ambiguous, drag is ambiguous, but one thing isn't ambiguous, and that's at the cruise condition. You're cruising along in level flight. There's no force on the aircraft plus the propulsor. It's cruising along. Velocity is not changing with time. F equals ma, so a is equal to 0, so F is equal to 0. Okay, so the force we're looking at is the cruise condition. That's the most important condition. Okay, so we have, what we're trying to do is to measure the power at one condition versus the power at another condition. So I used to teach the undergraduate projects course. We tell them when you do an experiment, it's not a really good thing to take two big numbers and subtract them to get another small number, right? The experimental uncertainty tends to increase that way. So that's what we're trying to do here, but we're forced into it by circumstances. So what we thought we would do is to try to get this measurement in two different ways. And one we'll call direct, and one we'll call indirect. So the direct method is to integrate over all the streams, upstream and downstream of the propulsor. So we have various rakes in the flow. Here's the potted configuration, nothing in front of it. Here's the boundary layer configuration, where the flow has a non-uniformity in front of it. And we're going to integrate to find what the mechanical energy is. The second way is we can measure very readily the electrical power going into the, well, that leaves the controller. And then we can do other experiments to find out the motor efficiency and the fan efficiency, so we can get, through supporting experiments, get what the mechanical power is. So this is a different way. It's indirect. We have to do experiments back at MIT, take the stuff back to MIT, and test the fans by themselves. But these are two ways to measure the same thing, and they got pretty much the same answer. One came out 10, one came out 11, something like that. But they were very close. So here's the experiments now. Talk about those. This is as fast as the tunnel goes faster than that, but basically the model couldn't take it. But so we had to put on various turbulence promoters. And here's the data collection force. All these things came from the NASA balances, the electrical power, and all the flow measurements we did. Okay, so here's unpowered. Okay, so that's the model in the tunnel. We changed the back of this. So about the front 75%, maybe a little bit more, remained the same. We had three different backs. This is the unpowered back. There's no propulsors on this. So what does this give you? This gives you the overall drag, basically. Overall drag and lift. Then the potted configuration, or the non-boundary layer configuration, has engines on the side. Okay, see them here? This is what it looks like, and that's the scale. And then finally, what we call the integrated, or the boundary layer configuration, now has the engines, or has the propulsors, on the top of the fuselage. So again, it was the last piece of this fuselage, but the propulsors, the actual propulsors, the fans, were the same device. So we wanted to get things as close as possible so that all the differences that we had to resolve would be small. So here's the back-to-back comparison that I'll show you. Potted versus integrated, and we write things non-dimensionally, but it's basically a coefficient for the potted, the non-boundary layer power, the boundary layer power divided by the non-boundary layer power at a given. And I tried very hard to get people to use what I considered rational notation, FH being the horizontal force. but there were some really dyed-in-the-wool aircraft guys, and they wouldn't allow me to change the notation at all, even though to turbomachinery people, this means the axial velocity. So I have to say that that's one I did not win. So if there's any confusion in nomenclature, tell me about it. I will relay it to my colleagues at MIT. Okay, so at a given force coefficient, which is going to be 0, that's what I'll show. And so here's our aviation week in our D8 in the wind tunnel in aviation week. We were really pleased with that. And also something I was pleased about is this is the MIT team in the wind tunnel. This is the diffuser of the wind tunnel. So far back here is the wind tunnel fan, this huge wooden fan. And here are the various participants. Okay, so I brought the team, guys. All right, so again, the experiment design was set up to facilitate, as it says, comparison. So front 80% of the fuselage propulsor units were interchangeable. So I'll show you 3 data charts. This is just the overall lift. So here's cruise. So this is alpha, angle of attack, the aircraft. This is lift coefficient, and here's cruise. So we took a lot of data here. There was a lot of repeat information, and it's virtually the same for all 3. For all 3, the unpowered, the non-boundary layer, and the boundary layer. Okay, here's the measured benefit. Okay, so what I plotted here is force here versus power coefficient here. So power is along that axis, force is along here, and what you see, there's a lot of data on it because all this, it just took us a long, this is, the students hand in their thesis with just enormous chapters on how difficult the experiment was. So I'm showing you how difficult this is. So allow me my one agony slide here. Okay, so this is non-BLI and this is BLI, and the data is it's really quite consistent. It repeated from year to year. We tried to make it on different conditions. Once we came back from lunch and a car had plowed into the wind tunnel. It was sitting there with a crumpled fender. Now what was it doing on the NASA gravel? I have no idea. But so we say even after the car, things didn't change. So here's about 9% benefit. Now this is the horizontal force, the X force. And at cruise, that's equal to 0. The balance measures nothing. This thing is going through the air, no net force on it. Thrust and drag are equal if you talk about a potted configuration. So what I've done here is expanded the scale for the cruise conditions, cruise mechanical power. So this is it's the same as before, but it's much expanded. And so you can see the behavior around cruise. You can see the repeat data. So 70, 84, 70 miles an hour, direct, indirect. All the stuff seems to plot together. So we got about a 9% benefit. So that's a substantial benefit for the configuration. But what does that mean, a 9% benefit? Because there's no unique definition or no unique way to define the boundary layer benefit. So what I've shown here is that the same sort of equivalent thrust, this is a curve of equivalent thrust, you have a non-boundary layer propulsor, and then you have different comparisons. And we use different nozzle plugs to get these comparisons. But this is the mass flow. This is the power. And at the same mass flow, you get a little over, well, that's the benefit. This is the estimated benefit you get, 6%, 7%. At the same area, you get less. At the same jet velocity, you get less. If you have the same power, you get the same number because you're comparing power. But basically, you can take the benefit out any way you want. That's a design-specific question. But at least we have now the tools and the understanding, the thinking, the rationalization to do this to do this comparison. And here's just a shot of the inlet rakes and just some of the instrumentation. We measured the inlet flow, the exit flow, in doing these experiments. Okay, just a couple of slides to show. Here's the inlet behavior, the inlet stagnation pressure distortion. So here's at 2 degrees, that's the cruise condition. And what you see is this is one propulsor, this is the other propulsor, and this is the fuselage shape here. Okay, so what you see is low velocity stuff on the bottom and higher velocity stuff on the top. This is all free stream fluid here. This is all free stream fluid here. This stuff comes from the boundary layer, slow moving fluid, low stagnation pressure. And there's a plot of what it looks like. Okay, so it's a very benign non-uniformity. At higher angle of attack, what you see is something that looks very much like vortices, right? I had vortices in my earlier slide, but the flow is swirling around here because the flow that comes into the boundary layer, into the engine, gets acted upon by the pressure field of the engine, and you have a non-uniform flow which is diverted in a pressure gradient, leading to streamwise circulation here, and thus you have a vortex coming into the engine. So this non-uniformity is something that needs further investigations. We didn't really think about this before the experiments, but this is an interesting offshoot. Okay, and this is just experiment computation. The computations work at the level of comparison that we're making. The computations work quite well. So I want to spend a little bit of time now on the second part, which I really didn't give its proper due. High OPR, high overall pressure ratio, high efficiency small core compressors. So if you take a compressor and you shrink it, you Photoshop it, the efficiency falls off really severely. And that's because not everything scales. The clearances scale with radius, but the blades, and so if you make everything smaller and smaller and smaller, the clearances don't get smaller. So efficiency limits and robustness to making the blades are like half the size of a dime. So part of the program was to look at this. How do you mitigate those effects? In other words, it does you no good to do boundary layer ingestion on this wonderful aircraft if the compressors are going to lose efficiency. And it's a mechanical issue also. You now have big fans. The fans are getting larger and larger and larger, and the cores, the part the hot stuff goes through, are getting smaller and smaller and smaller. How do you deal with that? So here's some charts from my colleague Alan Epstein. I think he probably showed these in 2013. But here's efficiency versus year of introduction, and here's core size. So core size is basically mass flow through the core. So you can think of it as core area, because the density is roughly the same. Core area is shrinking. The propulsive efficiency is going up because the bypass ratio is going up. The thermal efficiency is going up because the pressure ratio is going up. But it's this trend that you're really worried about. So this is the Pratt and Whitney view of the universe. And here's just another way to look at it. Core size. Current 737 engines are here, about 7. That's what a CFM56 is. So we're talking about going to 1.5, basically. So, and we're also increasing the pressure ratio. So we're talking about being up here, where it says advanced studies. Well, the thermodynamics is pretty clear about what that means. The thermodynamics is unequivocal. It's also unforgiving, right? So you have to get things right from point of view of component efficiency and from point of view of mechanical living in this environment. Okay, so here just to show the problem in a different way, here's a photo scale of a CFM56 and of a D8.5 engine. So the fan is not much smaller. The bypass ratio, which is the mass flow going through this core part to the mass flow going through the fan part, bypass ratio is a factor of 2 or more larger. And you can see the many stages, higher pressure ratio, and you can see it's getting really small in the last few stages. Means things like clearances get really important. Leakages get really important. And so you're in a situation, and again, I'll defer to my colleague, where design practice says this. Here's relative size, and here's the area we want to be in. And the efficiency is starting to dive off. But there's nothing that says, from a fluid dynamic point of view, the Reynolds numbers change a little bit. There's nothing that says, from a fluid dynamic point of view, that you can't do this. So that's what he means, physics versus design practice. Okay, so there are challenges, and this is another thing. There are challenges in these high-efficiency, small-core engines. One of the challenges is something called the 1 in 20 rule. Anybody here would know what the 1 in 20 rule is? This is an FAA rule. It says that if a turbine disk bursts, you can't contain the turbine disk. There's too much kinetic energy. You can contain fan blades, but not the turbine disks. If a turbine disk bursts, I think they tend to break up into 3 big chunks. It has to be less. That happens very infrequently, but it has to be less than a 1 in 20 chance of taking out either the other engine or some flight critical part of the aircraft. So how do you do that? Because our engines are really close to one another. If you do, it's just sort of the subtended angle. It's more than 1 in 20. So the Pratt guys worked really hard on configuring the engines, and they created a new and innovative geometry. There's a SciTech paper about it, which I can give you the reference if you email me. And they actually obeyed this 1 in 20 rule. So we have that. We have close-coupled exhausts. We have propulsive efficiency with boundary layers. And more so, the biggest one is performance of small-core turbomachinery. What's that performance is going to be like? And taking a step back, what's the engine architecture going to be like for these small cores? You can't fit the low-pressure shaft through the small core, so it has to be different than all current engines. But you can look at this in the paper. So I have a couple of conclusions now. So what did we start out to do? Address impact of BLI and advance the technology readiness level. So it's the 3 of us plus NASA, the 3 partners plus NASA. This was a real stretch program, I thought. I was just, at the beginning of it, I was just hoping that we would be able to go into the NASA tunnel and not embarrass ourselves. But it came out really well. So I thought it was great. High payoff, new technology challenges. And what's come out of this is that if you look at a different product, you now have different things to work on. And that's a point that Epstein made in his Dryden lecture, which I thought he gave here. So the problems you're starting to look at now are different. They're new and exciting, and that's always good news for an academic. So back-to-back comparison. And again, power at simulated cruise as a fuel burn surrogate. Okay, so what else did we do? Well, 15% system-level fuel burn savings. Our measured behavior was about 9%. We, as I said, measured at 2 different techniques. And so we think that this is really strong support for the question of boundary layer ingestion, not only for the D8, but boundary layer ingestion for maybe different configurations for civil transport. So where are we going? My last chart. Well, it's now MIT, University of Michigan, USC, and UTC. Why USC? Well, one of the research engineers is now a professor at USC. UTC is United Technologies, and University of Michigan. Professor Martins is also working with us, and I was pleased to meet him for the first time today. So what are we trying to do now? Well, it was low speed calculations, trying to evaluate the benefits at high speed, define the configuration for cruise Mach number. What turbomachinery attributes do you need for these distortion-tolerant fans? And what are the features? What does distortion mean? And also, separate program, Aurora is now working on the design of a possible flight demonstrator. Don't know if this is going to happen, but they're working on the design. And so here's the bottom line. It really is the bottom line. I thought, and I think the students and the other faculty, we really thought this was an exciting project. And again, we're trying to change the look of civil transport aircraft. It's about time, isn't it? And the way industry thinks about aircraft and also propulsion. So with that, let me just acknowledge NASA program, team members, our partners, Harold Youngren, the staff at NASA Langley, they were super, and the NASA project management who were with us through thick and thin. And I have to give them a lot of credit also for having faith in us. So thank you very much, and I'll be glad to take any questions.
So the Cadre satellite is a precursor satellite to a future mission called Armada. We're going to have a large constellation of satellites that go up to low Earth orbit and study the atmosphere. So before we put the spacecraft on the rocket, there's a lot that goes into testing it.